this to you better. Okay, so let me draw the three limb code type transformer, three limb code type transformer which I am drawing here right now. Is similar to the code is similar to the cell type single phase transformer, but which I am drawing it is three phase three phase three limb code type transformer. Okay, and then you will have the windings as it is a three phase transformer, so you will have six coil, 3 to just 6. For each phase you will have one low voltage, another high voltage winding, or one primary, another secondary winding. So as a whole you will have six coil wound on it. And the terminals will be marked with, suppose it is the primary and this is the start, so we can write the start of primary for phase A, and this is the finish of primary of phase A. Now this is the start of secondary phase A, and this is the finish of secondary phase A. This is the start of primary of phase B. This is the finish of secondary, sorry, primary phase B. This is the start of B, and this is finish of B. This is S, C. This is F, C. This is S, S, C, and this is F, S, C. So this is how we have six coil, two coils are wound on each limb. There are three limbs, so therefore we have 3 to just 6 coil. Now, if we have 6 coil, how many terminals we have? Number of coils?
Into two, sir.
Huh?
12 terminals, sir.
Okay, so number of terminals, 12. So this is common for all three-phase transformer, because all three-phase transformers should have at least 6 coils and 12 terminals. Okay. Now here I will draw a different thing, that is the flux. Now the phase A, if the phase A is excited either by the primary coil or the secondary coil. So if the phase A is excited, then how the flux will be generated? So suppose this is the phase A flux. So phase A flux will flow like this. It is also will flow through this part of the core. So, So this is the phi A. This is also phi A. Now for B phase, fractional hai. So the phase B flux will flow like this. So this is the phase B, though it will be halved like this. So this is phase B by 2 and this is phase B by 2. Okay. And the last one is the phase C flux. That is also that also will flow like this. And this phase A and C has some similarity. Okay, so this is how you see, which I have drawn here, the flux lines for all the three phases. So, so I have used this color. I have used red color. I have used this red color. I have used this orange color, and all the colors you can see. Uh, so I have used the green color. So I have used the red color for phase A. I have used the orange color for phase B. I have used the green color for phase C for all the fluxes I have drawn here. So you see at every point on the core you have the contribution of all three phase fluxes. Okay, so you won't find any point on the core where you will not find the contribution of any one flux. So that means you can say that at every point you will have the contribution of all the three phases fluxes. So that is the main property of this type of code type three limb transformer. And one question I want to ask you that when I when we excite phase A or phase B or phase C, now we need some magnetizing current because magnetizing current generates the flux that you know I think. So magnetizing current is required to generate the flux inside the core. Magnetizing current. Okay. Now you know that for A phase also you need some magnetizing current. So B phase also you need some magnetizing current. And for C phase also. Okay. So for all these three phases you need magnetizing current to generate the flux. Now can you tell me if we have the same flux generated by all the three currents? The flux is the same. That means all these three fluxes are same. So phi A equals to phi B equals to phi C. All the three phases flux are same in magnitude. That means their Weber value, flux units is Weber. So all these three fluxes values are same. Now, in which phase we need the minimum, or in which phase we need the maximum magnetizing current? So that means among these IMA, IMB, or IMC, these three magnetizing current, which is minimum or which is maximum, and whether all the currents are same or all the currents are different if we have the same flux band. So this question I want to ask you. Anybody is there? to answer this? Is anybody there who can answer this? Shaurin,
Yes, sir.
do you know?
So magnetizing current same हवा को था.
For all these three phases, you are saying that magnetizing current will be same. Okay.
Yes, sir.
Anybody else? Moumita Kundu. Moumita Kundu. Are you there? Moumita Kundu, are you there? Speak out. I can't hear you. Okay, so you will not answer this. Chiranjit,
Yes, sir.
will you try this question? Have you listened the question? Which
Sir, magnitude will be same. Sir, magnitude will be same.
why?
All of the phase.
Why? Why?
Sir, because flux, all the flux is same. So I think
All the fluxes are same, but
phi A, phi B, and phi C, all
you
magnitude are
keep
same. So
magnetic. You know how the fluxes are generated. Who generates the flux? ফ্লাক্স কিভাবে তৈরি হয় জানো?
alternating current জন্য
না, ডাইরেক্ট কারেন্টের জন্য ফ্লাক্স তৈরি হয়। কে বলেছে তবে অল্টারনেটিং কারেন্টের জন্য ফ্লাক্স তৈরি হয়? ডিসি কারেন্টও ডিসি ফ্লাক্স তৈরি করে।
sorry
অল্টারনেটিং কারেন্ট
current
ফ্লাক্স তৈরি করে, কারেন্ট মাত্রই ফ্লাক্স তৈরি করতে পারে। হোয়াট ইজ দ্য মেকানিজম বিহাইন্ড ইট? Okay, so actually the current first generate the mmf. Okay, so currents solely cannot generate the flux, because when the current flows through a coil having n number of turns, then it generates an mmf. So this I into n is called the mmf. And now this mmf produces the flux. Okay, so mmf means magnetomotive force, which is responsible for the flux. Now, whether the flux will be same or different, that not only depends on the mmf, because as these uh, fluxes are same, so if only mmf is responsible for producing the flux, then the mmf would have same. But for this case, it is not true, because though the fluxes are same here, but the path of the fluxes are different. So if you observe the flux paths carefully, then you will see that the A phase flux is the A phase, rather A phase coil is at one end and C phase coil is at another end, isn't it? So, and the B phase flux is on the middle, on the center. Now, when A phase is producing some flux, it has to flow the flux, its own flux through the next limb, but the other limb is far away from it. That is the limb allocated for C. যখন A phase flux তৈরি করছে তখন ও ফ্লাক্সটা কোথা থেকে ফ্লো করাচ্ছে বি ফেজের লিম্বটার মধ্যে দিয়ে যেটা ওর কাছেই আছে কিন্তু সি ফেজের লিম্বটা অনেকটা দূরে আছে is far away from it. Now the same is valid for C phase also. When C phase is producing some flux, it is flowing through a nearest limb, that is the B phase limb. Not only that, it is also flowing the furthest limb, that is the limb allocated for phase A. Okay, but this is not the case for phase B. For phase B, both the limbs are at the same distance. Will you have you observed this? এই জিনিসটা লক্ষ্য করেছো যে বি ফেজের রেসপেক্টে দুটো লিম্বই কিন্তু একই ডিস্টেন্সে আছে কিন্তু এটা এ বা সি ফেজের লিম্বের জন্য নেই ওকে so that means for B phase the magnetic potential drop is less compared to other two phases. Okay, so therefore the B phase needs the minimum mmf or minimum magnetizing current to produce same amount of flux at each point on the core. Have you understood this point? সোজা ভাষায় বলতে গেলে এ ফেজের ফ্লাক্সকে এবং সি ফেজের ফ্লাক্সকে অনেক বেশি দূরে দৌড়তে হচ্ছে তাহলে এই অনেক দূরে দৌড়েও যদি ওকে সেম ফ্লাক্স মেনটেন করতে হয় তাহলে তার এমএমএফটা অনেক বেশি হওয়া উচিত কিন্তু বি ফেজের ফ্লাক্সকে কম দৌড়তে হচ্ছে সেই জন্য বি ফেজের এমএমএফ রিকোয়ারমেন্টটা কম ওকে so that means this mmf will be the minimum. So have you understood this point?
হ্যাঁ স্যার।
বুঝতে পেরেছো এবার
হ্যাঁ স্যার।
চিরঞ্জিত
হ্যাঁ স্যার বুঝতে পেরেছি হ্যাঁ স্যার বুঝতে পেরেছি স্যার
হ্যাঁ এইটা কেয়ারফুলি বুঝতে হবে সেই জন্য আমি জিজ্ঞেস করছিলাম why how the flux is generated that you should understand clearly so how the flux is generated in a core so for flux we need mmf not only the current okay so current is remember the current is an electrical variable electrical quantity but mmf is the magnetic quantity flux is the product of magnetic circuit okay and the current is the product of electrical circuit so there are two different things one is the magnetic circuit another is the electrical circuit for electrical circuits variables are voltage current power etc and for magnetic circuits the variables are mmf flux magnetic field intensity flux density etc etc so these are the variables which we use these are the terms which we use for magnetic circuits only so two things are different electrical circuit and magnetic circuit and remember if you don't understand the magnetic circuit for any machine then your understanding will be incomplete because in all the electrical machines there is a complete magnetic circuit it may be transformer single phase it may be three phase transformer it may be DC machine it may be three phase induction motor any machine there should be a complete magnetic circuits and you have to understand the magnetic circuits first not only electrical circuits okay now I will next I will draw the circuit so another variation of this code type is there, that is also available in market, and that is called the 5-limb code type structure. So that also I will draw. So 5-limb is 1, 2, 1, 2, 3, 4, and 5. Okay, so this is 1, 2, 3, 4, and 5, and the windings will be only here, like this. This structure is also used for some cases. These are called three-phase 5-limb, but this is also code type transformer. Remember, this is not cell type. This is also three-phase 5-limb code type transformers. Okay. So here almost the magnetizing currents are balanced, because here the magnetizing current can flow to an additional limbs. Okay, like this, like this. Okay, so this is another structure. Then the shell type structure. Let me first draw, then I will explain. Somebody raised his hand. Is it intentionally?
So can I ask a question?
জিজ্ঞেস করতে পারো, বলো।
So what is the main advantage of 5-link code type transformer over 3-link code type transformer?
Okay. So as I mentioned there, the flux paths are balanced, and other advantage I will not, or disadvantage, advantage I will not discuss now. So from the flux point of view, as I mentioned here, the magnetizing currents are almost balanced for these three phases. Okay, so disadvantage, you can say that it needs more iron for this 5-limb code type. And one more disadvantage is there from the harmonics point of view. So I will discuss all these advantages and disadvantages in due course. Okay.
Okay, sir.
স্যার একটা কোশ্চেন করবো?
বলো।
বলছি স্যার ওই থ্রি ফেজ 3 কোর লিম্বে যে আপনি বললেন যে যেটা বোঝালেন, ওখানে যে বি ফ্লাক্সের এমএমএফটা একটু মানে খুব কম কারেন্টের জন্য ম্যাগনেটাইজ হচ্ছে, মানে আদার্স বি আর এ আর সি এর জন্য, মানে সি এর থেকে। তো ওখানে কি এনআইটা তাহলে আমরা কি করে ব্যালেন্স করি?
কোনটা?
থ্রি ফেজের যে এনআইটা আছে,
হুম।
মানে এমএমএফটা এর ফ্লাক্সের জন্য আর সি ফ্লাক্সের জন্য তো দুটো সেম। বিটা
ব্যালেন্স করতে
যখন
হবে কেন তোমার? একটুখানি ম্যাগনেটাইজিং কারেন্ট ইজ very small compared to the load current. When they are in the full load condition, na,
হ্যাঁ,
so you don't have to balance that. Slightly
Okay, sir.
different kind current it will be taken by the B phase. There is a magnetizing current.
ওকে স্যার, থ্যাংক ইউ।
You don't have to, it will be taken by the B phase, or মানে B phase নিজেই কম কারেন্ট নেবে, এটা তুমি
হ্যাঁ,
ব্যালেন্স করার জায়গায় তো নেই।
আচ্ছা স্যার।
So this is the cell type structure. ব্যালেন্স কখন করতে হয়? যখন অনেকটা ভেরিয়েশন হচ্ছে, যখন ফুল লোডে দেবে তখন তো ম্যাগনেটাইজিং কারেন্টটা এমনি খুব কম থাকে, জানো তোমরা নিশ্চয়ই, মানে অনলি 2% of the full load current, or even less, because নো লোড কারেন্টের 2% হয় এবং তার মধ্যে আবার ম্যাগনেটাইজিং কারেন্টের একটা পার্সেন্টেজ থাকে। ওকে, তাহলে সেই জন্য সেটা খুবই কম হয়, সুতরাং সেটা নিয়ে বেশি করার দরকার নেই। So this is the start of a phase. This is the finish of a phase. This is the start of secondary of a phase, and this is the finish of secondary of A phase. This is the start of primary of B phase. This is the finish of primary of B phase. This is the start of secondary of B phase, and this is the start of primary of C. This is the finish of primary of C. This is the secondary C, and this is the, sorry, okay, so this is S and this is F S C. Have anybody asked anything? Okay. So these are the coils. Here also you will have 6 coils and 12 terminals as a whole. And here the 3 limbs. So here you have a number of limbs, 3 limbs for each phases, and total 9 limbs altogether. Okay, but only 3 limbs out of these 9 limbs are used for the coil. Okay, and the rest of the limbs are there for flowing the flux. And for A phase, the flux will flow like this. So this is the flux lines for A phase. You can say this is flux lines for A, and this is for B. So this is the flux lines for B, and this is the flux lines for C. So I have used the same color for 3 phases fluxes. That means I have used red, I have used orange, and I have used green for denoting the phases. This is for A phase flux, this is for V phase flux, and this is for C phase flux. Now here the figure is quite clear. Clear means quite clean, you can say, compared to the previous figure. The previous figure, the figure for the code type transformer or 3 limb code type transformer, quite um, clumsy, because we had to draw all the lines everywhere. Okay, so figures a little bit clumsy, but here the figure is little bit clear. So from that you will understand very clearly that everywhere inside the code you don't have the contribution of all phases flux. মানে কোডের সমস্ত জায়গায় প্রত্যেকটা ফেজের ফ্লাক্স আছে এরকম নয়, আনলাইক দ্য 3 limb কোড টাইপ। 3 limb কোড টাইপে আমরা দেখেছিলাম যে কোডের যেখানেই যাব 3টে ফেজের ফ্লাক্স পাবো। এখানে কি, এখানে অ্যাডিশনাল লিম্ব গুলো থাকার দরুন ফ্লাক্স গুলো ফ্লো করার পাথ পেয়ে যাচ্ছে। Okay, ফলে here we have some limbs, here we have where we have the contribution of only one phases flux, but there are a few limbs where you have the contribution of at least two phases flux. And if I want to mark it, so these are those limbs where we have the contribution of two phases flux, not only one. So we have contribution from two phases, isn't it? Otherwise it if you can see that only one phases flux are present.